Thank you, Gustav, for the third introduction in a series of 3 very informal brown bags. Today, even though we're in this beautiful room and we're online, it's also an informal talk, very much work in progress, but we're doing it online so that more people can join. So thank you. It's my chance to say thank you to the Vienna Institute of Demography for hosting me these last 6-8 weeks. It's been a great fun. This is all, actually, most of the work I presented here is fairly new. It's things I've been working on here. So this was super exciting. I started this, I think, during the migration conference. I was scribbling notes next to, I think, Gustav on this. But this is actually a longer term project with a student at Berkeley, Niklas. I taught formal demography last year, mathematical demography, and this turned out to be a project that Nick worked on, and he's going to present a poster on this at PAA. What else should I say? I should say that in my first talk on momentum, I kind of questioned whether momentum had to exist or not, and I did things with turtles and trees and things like that. And now you have to just forget that talk, pretend like momentum is as you always thought it was, because that's how I'll treat it here. Okay, and as Gustav mentioned, we'll be looking at a different flavor of momentum. We'll use the traditional fertility momentum from Kiefertz, and we'll compare it to momentum from migration. Okay. This is an interesting topic. It's kind of what we're going to, we have, the world around us is kind of we want to escape it into science because of all these terrible things happening in the world. And so science maybe is some kind of escape from the world. A lot of great mathematical, formal demography, demographic discoveries were made during wartime. Bernardelli and the Leslie matrix and Beatles was in the 40s. Feller proving renewal theorems in the 40s or something. So we're in this kind of chaotic world situation, and it would be nice to disappear into science. And this is a nice thing to disappear into, but as we'll see, migration is a very political topic. So even though we're going to be kind of formal demography talk, there's a kind of a social, economic, political kind of aspect to this, which really needs to be added to this formal part that I'll be talking about today. Okay, so I'll talk about I'll specify the question a little bit better. I'll just, about slide 3, I'll give you the answer. I'll just use I'll just do a little simulation with Austrian demography and show what the answer is. And then we'll try to understand the answer. And then I'll talk about extensions, which is always fun here because whenever I put up a list of extensions, somebody grabs one of them and writes a paper about it, often published before my original paper is even done. And then we can have a discussion. Okay. So, what is population momentum? Well, one way to think about population momentum is the way that Kiefertz defined it, which is that you have a sudden change in demographic regimes at some time. It's called t equals 0. And in the Kiefertz case, it's fertility rises to replacement levels. And then what happens to the population size is the question. And the answer is you get some ratio of the final population size, the stationary population, to the population when you change the rates, the starting population size. Okay? And Kiefertz kind of formalized that, but it was already, as Gustav mentioned, a known phenomenon that because of age structure changes and changes in the number of births, you would have continued change in population size for some time, even after you put in this replacement regime. And in the case of a growing population that was growing exponentially, it would kind of flatten out slowly and end up higher than when you put in the replacement regime. In the case of a shrinking population, it wouldn't get flat immediately. It would keep going down before it flattens out. Okay, so that's what we mean by momentum. Well, we don't have to, there's other ways to get replacement fertility, right? If we have a growing population, we could reduce fertility, we could increase mortality, or we could send people away. We could have out migrants. And in a shrinking population, we could increase fertility, which is what we're all talking about around the world. We could increase mortality, increase survival, so we live longer and we get more people, or we could bring in migrants. And that's what I'll talk about today. We'll have an immediate change. We'll have a population that has no migration. Just to make it kind of concrete to think about, let's think of a shrinking population that decides to bring in migrants. Okay, and we'll ask what happens to the population size. Is there something similar to momentum as with fertility? And what's going to happen to the age structure, the evolution of the age structure? Now, this is a new area, an old area. It's not new at all to study migration. It's a topic, of course, an important topic in population studies, and also an important topic in the narrow area of formal demography. And there's been a number of really important, very interesting papers. Espen Schade is a pioneer here. Carl Schmertmann, I think with 1 T and 2 N's, apologies, has done great work in this. The model that we're going to be using was introduced by Alho. But these models are about kind of the stable state and the age structure in the stable state. And here we're going to look at kind of transitional dynamics. We're going to have a population without migration, that we're going to have that same population where we introduce migrants, and there's going to be population waves and things, and we'll get a population size and a structure that results. So what's new here is this kind of transitional dynamics. And I should say, even though we're on Zoom and we are in this huge, beautiful room, we should treat this like a brown bag, and people should interrupt, ask questions, do all that kind of thing. We have, what, an hour total?
To go 45
we have 45 minutes to go, yeah.
Including discussion.
Yeah. Is everybody okay here? Okay. I mean, I'm not going to get that much into the technical aspects of this, but in order to have this all be meaningful, we need some kind of renewal aspect. The population at time t+1 has to come from the population at t in some formal way. Obviously, you could just bring in any number of migrants you want, and it could have nothing to do with the time at the previous state of the population. And then the question doesn't really have much of an answer. So you have to have some formal system. And I'll sketch out what the relationship is here, but I'm not going to get into it in great detail. Okay, so this is our question. Is there momentum? And here's just a simulated answer. The answer is replacement migration, as opposed to replacement fertility, has less momentum. So what I did was I simulated a stable population using Austrian fertility and life table. And I'm assuming on the screen you can see this, my little mouse. You can, right? They can see this, what I'm doing? Yeah, okay. Here's the population of Austria. Again, there's no migration. It has the fertility of 2023, the survival of 2023, and without any migration, the population would be declining, I think a little more than 1% a year. The Austrian population isn't declining, particularly because it's not stable and because there are migrants. But if it were, it would be declining like this. And then at time 0, we change the demographic regime. We either do the Kiefer scenario of replacement fertility or our scenario of replacement migration. And we see the usual fertility scenario. The population does become stationary, but only after declining to about 2/3 of its previous value. So that's the usual population momentum. And when we do this with migration, we also see there's momentum, but it's, I don't know, a half, 2/3 of the amount. Here I'm defining momentum as kind of the gap here. And what is 1 here? 1 is just the population size. I just set it to 1. You can do 1 times, how many people are in Austria? 9 million? 1 times 9 million, you can call it. Yeah.
Sorry, but what level of migration do you assume here?
Okay, so the way this is going to work is we're going to have migrants come in. In our setup, migration is complicated because babies are relatively easy. They all arrive at age 0. Migration, people can arrive at any age. So we're going to have them arrive at any age. And here I'm having them arrive at 18. And we'll talk about whether that's a useful assumption or not. But all migrants arrive at age alpha 18. And how many migrants come? Well, that is just a function of the net reproductive rate, we bring in enough migrants so that the kind of effective net reproductive rate is 1.0. Now, this idea of these kind of more general net reproductive rates is around. I think Preston has some papers on it. There are probably a number of different papers on it. But is that informal description enough for you, Wolfgang? Okay.
And mortality and fertility of migrants is the same. Like
yes. Good. Yeah. Yeah. Okay.
I have also a side remark. It's interesting if you consider the Kifid's, the blue scenario. Kifid considered in Bucharest when he gave the Formula 74 this increasing population. Brazil was the example,
yeah.
And countries, and there was 1/3 more. This was the factor was 1.6, and here is 0. So it's interesting enough, rather symmetrical.
Yeah. Interesting. Yeah, the magnitude here. Okay. Okay, so we could just stop here. We have the answer, but of course, why? So we're going to answer why. Okay, so let's again just look at the simulation, and we can kind of get the answer from the simulation, at least in one sense. Okay, so the population size, let's not look at the slide for a second. The population size in a stationary population is going to be the number of births times the person years generated by each birth, which is usually the life expectancy. But in this case, the person years generated by any birth are going to be the life expectancy of the born person plus the life expectancy of the migrants generated by that person in some sense, because migration is proportional to people. Okay, so if the population is bigger for migration, it could be because there are more births after we play this out through time. It could be because there's more people per birth. Or it could be, so it's some combination of those things could be going on. Okay, so let's look at what's happening here. So it turns out that when you have a stationary via migration population, it will have fewer births in the long term than the stationary by fertility population. Okay, so let's look at the blue line for stationary fertility. So what happens in the Kifid scenario? The NRR suddenly goes up, you get a lot more births, you get a huge baby boom, and then kind of you have these waves, and it turns out you have more long-term births in the stationary state than you did before we started. That's the kind of one of the paradoxes of momentum, is that you get population growth even though you have fewer births. Well, why do you get that change in population size? Because the age structure changes. Okay, so here we have a shrinking population. So the usual Kifid scenario has more babies in the stationary state than we had in the starting state. Okay. Interestingly, and this is what I discovered last week or the week before, in the stationary via migration population, there's almost no change in the number of births. I don't really have great intuition about this. It kind of a number of things, at least in my models, a number of things kind of cancel out to give us this result. And it doesn't have to be true, but it's true if you have this setup and you have migrants who enter before they have children. Okay, so what's driving the bigger population of the red line compared to the blue line is not that there are more babies, there are actually fewer babies. It's that there are more people per baby. The migrants come in, and you have a lot more older people. Because here migrants come in at age 18, and so you have some constant number of births in the stationary population, and then suddenly at age 18, people come in, and then they have the same life table. So it just kind of follows them. Okay, and notice that this is half an H pyramid, so the whole population is the area. Both of them are smaller than the original stable population. What else is interesting? It's kind of interesting, these all cross at the same point. There's a bunch of technical papers about crossovers. What else is interesting? Well, as we're going to see, dependency, we can think about dependency. Let's forget the black line for now and just look at the red and blue line. Well, the red line is going to have a lot less youth dependency, because there are fewer young people. It'll have the same old age dependency because this above the age of migration, these curves are just proportional to each other. So there'll be a dependency advantage, this is very interesting if you're kind of thinking from the national transfers perspective, or if you're thinking from the education perspective. So all these things that the people in the back of the room spend all their time thinking about, or a lot of their time thinking about. Other questions here? Yes, Mark.
Yeah, just thinking about this little change in the number of births
Yes.
in the migration scenario. Because when I look at the age structure, it means that approximately from age 18 on, 1/3 of the population seems to be migrants.
Yes.
But then also when you have the same fertility, like the immigrants, also 1/3 of the children should be migrants.
Yes.
Yeah.
Good.
So I do not understand why this, but it's compared to the stable population. Okay, right. Yeah. Okay.
No, but your point, I think your point is very good. There's quite a few migrants, because fertility is pretty low in Austria, and you need quite a few migrants to get to stationarity. And you get something like 1/3 of the people aged 18 are going to be, and above are going to be foreign-born in the setup. And all of these people are native-born, but about 1/3 of them come from the migrants. It's not terribly different than the current regime now in Austria. Okay, so how do we explain this picture here and this picture here? So the model we're going to use is based on Alho's setup, Alho's setup. We're going to do a simplified version. He has immigrants arrive at any age, but we'll just have concentrated immigration because that's a lot easier to think through. So we'll have immigrants arrive at a single age alpha. In the previous slides, it was 18. And then the immigrant rate is going to be proportional to the number of sponsors who are themselves aged alpha. So a newborn, we'll do female dominant population. So we'll have a newborn baby girl, and we'll use alpha as 18. And she'll grow up and she'll just survive until she's 18, till L18 she'll have an L18 chance of surviving. And then at age 18, she will produce she'll produce some fraction of her as migrants. Okay, and so we can kind of think of this as sponsoring or something like that. And the migrant that she produces will be the same age as she is. And then they'll both begin having children and all of that. Okay, and so the lifetime production of a person, of a newborn baby, will be that she'll have NRR babies herself, plus she'll have C migrants aged alpha. And what we set C at is going to determine the long run growth rate. And we can choose C so that the long run growth rate will be 0. And that is the scenario that we implement. And that's the simulation is based on choosing the number of migrants, so the long term growth rate is 0. Okay, so how does this work? We're going to try to do this as much like Kiefer's as possible. So we'll begin with a closed stable population, which is what Kiefer's did. We'll start everything in the period time t equals 0. Instead of having fertility go up, we'll have migration begin. And we'll choose the level so that C equals C0, which makes the long-term growth rate 0. Or another way to think of this is it makes kind of this generalized NRR equal 1. Okay? And after some transitional waves, the births and the pop size will become stationary. So that's the setup. So you can analyze this. You can write out a renewal equation for this, where today's babies come from yesterday's babies. Actually, they come from yesterday's babies and yesterday's immigrants. But since the immigrants themselves are proportional to yesterday's babies, you get a nice renewal equation. And then you can do all of the usual formal demography with renewal equation, and you can look at what the limit of births is. And it turns out the limit of births in the setup, 0 is just the time when we started the scenario. So that's when the black line ends and the red and the blue line begins, time equals 0. It turns out that the ratio will be e to the r alpha times e to the minus r mu over 2. Well, this is the square root, this is 1 over the square root of NR. mu is the mean age of childbearing. And if alpha is about the same as half the mean age of childbearing, this will be about 1. So this formal result explains why these numbers are very close. Now here it's 18. 18 is not exactly half of the mean age of childbearing. The mean age of childbearing is about 30. So it's not exactly the same. Okay, so that's what, of course, I'm not going to show, but that's what I went through with Gustav and Thomas a few days ago. And I actually have a little more intuition of why that's the case, but I think it's much too technical to explain here. Okay, so what's the intuition on age structure? Well, there's actually a big literature which Caswell has a lot on in his book on animal populations about sensitivities and eigenvalue sensitivities and things like this. And they do sensitivities not just to fertility, but also sensitivities to mortality. And so there's a big study of this already. And it turns out we can think of the Alho model as, and as he himself points out, as being a closed model where there's no immigrants, but instead what happens is you have a very strange survival curve. So here's a survival curve of Austria, where basically, thank God, we're all staying alive until 60. That's a good number to stay alive until. And then chance of living longer goes down. And then we can think of the dynamics as being generated that we're doing with migration as being generated by a closed population with this L star curve instead of survival. Well, L star is a very bad survival curve, because what do we learn in demography? We learn that survival curves are bounded between 0 and 1. So it's not really a survival curve. That's why I have cohort survival in quotes, okay? But it's kind of like per newborn, how many people are you going to get of this age when you come back that many years later in your cohort? And the answer will be, you'll get about 1 until age 18, and then starting at age 18, you'll get about 1.6. And of course, that number will decline as the immigrants who come in at age 18 also die proportional to the newborn, the native newborn. Okay, so one way to write this formally is we just say that L star of A is LA for all ages less than alpha, and LA equals 1 plus C. I should have written C0 here, because if it's C0, then it turns out it's the LA divided by the NRR. And this looks extremely Kiefertz-like, because what does he do when he does his fertility scenario? He divides the baseline, the stable fertility, with some non-zero growth rate, by the NRR to get an NRR of 1. So we're doing the same thing. We're just, in some sense, dividing survival. This looks a little strange. We're dividing by the NRR, which should make things smaller, but this gets bigger. Well, why is that?
Because it's below 1, the
Because yes, in this case of Austria, all of my figures are generated by an NR less than 1. So we're dividing by something less than 1, which inflates it. But the whole model would also work in reverse. If we had a growing population, instead of bringing in migrants, you'd export workers. Questions here? And when you do the formal analysis, you just use this L star function instead of the L function, and then you can do all the analysis. Yes?
I have a question, but this remark, maybe this would fit more at the end, but I would like to pose it here. It would be very valuable if you could replace this single alpha by the distribution which is actually empirical in Austria.
Yes.
Not a single age of immigration rather than this interesting two-peaked immigration scenario. And in that case, I'm aware that you cannot use this Feller's renewal theorem where you divided PT over P0 and the limit on that, this mu over 2 and so this would not work anymore. I'm aware of
Well, it would work. It just would be harder to to get nice results from. You can write it all out, but it's just there's a lot of math to do. So I have Nick with me. He's my co-author. He's going to do it for PAA. I will make an argument, though, that actually this is not such a terrible loss of generality to say that immigrants arrive at some age like 18. I'll make that in a minute. Also, you can simulate anything you want. And I was going to present the results of the full age structure of immigration, and they're not terribly different. And we can talk about why they're not terribly different. Now, this is fertility momentum. When you have children and you become an empty nester, your children still call you. If we had, say immigrants come gradually from age 18 to 28, then this would kind of, instead of going up suddenly, it would go up slowly. So you have kind of a rise and then a fall. And maybe people have seen these papers about the formal demography of stable populations with immigration, have kind of familiar with this kind of hump type shape thing. Okay. So where are we? Momentum is smaller in the sense that the difference between the change in the population size. So I'm saying that 0.78 is smaller than 0.65. It's not. In what sense? It's less different than 1 than 0.65. It's farther away from the gray line. Sorry, it's closer to the gray line. So momentum is like the distance from the gray line. So momentum is smaller. It's not because of the birth stream effect. The birth stream effect actually goes the other way. You should have, if you had the same survival curve and fewer babies, you would have fewer people, not more people. The key mechanism is the age structure. You have more people per birth. And so the sum of the L stars is much bigger than the sum of the L's, because it has that big extra portion that you sum up. And in fact, I think in the note I wrote with Gustav, I wrote something like E star 0, and it's like 138 in this example. And he said, well, that's not a life expectancy. No, it's not. So E star 0 is a bad notation to use because it's not a life expectancy, but it's the number of person years generated by a birth. It's not how long a person will live. Okay, so that's the basic momentum story. Well, the story is actually more interesting than this because you have, of course, dependency. Why are we interested in population size anyway? It's a good question. I'm sure we could have a long discussion with Wolfgang about why we should be interested or not interested in population size. And I recommend his book a lot on that. But more or less demographers have said, well, population size, it doesn't really matter so much. Age structure, that's what's really interesting. So let's look at age structure, and we'll just use dependency ratios here. I think I'm using youth goes till 20 here, so it's not standard definition, but okay. So here's our usual fertility scenario. Let's try not to look at the red, we'll look at the blue. Well, what happens? These little dots here are the youth dependency ratio. The big numbers are bad in the sense that you have a lot of dependence per worker, per percent of working age. So what happens? When you increase fertility, you increase the youth dependency ratio from the earlier stable state. However, you have a smaller fraction of the population who's elderly, and so after a while, the old age dependency falls. And the combination of this is you have kind of like a negative dividend to start with. Things get really tough when fertility increases for a little bit. And then it kind of plays out and you start getting the advantages from having a smaller fraction of the population be elderly, and you end up with actually lower but about the same dependency as when you started with your shrinking population. So that's the fertility story. With the migration story, you get essentially the same curve. It's a little bit different at the beginning for the elderly, because remember the two things are just parallel, the red line and the blue line and the age parameter is parallel. But kids, there's basically no change. So you don't get this increase in the youth dependency ratio. And so what happens is you don't have that kind of negative dividend to begin with. Instead you get a positive dividend, and then it kind of stays that way. Yes?
I think, Josh, I fully agree. I think as long as you call this demographic dependency, but I would not agree if you call this economic dependency, because from the NTA we do know that the economic characteristics are very different. I mean, of course, here you assume that a migrant is the same like an Austrian, but I think in terms of really real data, I think having no fixed age structure, but letting the age determined by the economic characteristics, you would get very different results, I guess.
Well, I think I would change the emphasis a little bit. Obviously something to explore. Just simply expand to another dimension with something like education, and you get something very interesting.
Yeah.
And it's kind of waiting for this group to do that, kind of. Whether that's worth doing the formal dynamics of, or whether it's just kind of there's more simulation is a good question. Of course, a lot of these things are already investigated. The National Academy report, done along, they did 2 editions of, investigates all these things, kind of using NTA type things in great detail. And I'll talk, I actually have a point that I'll make about this in a second, but yeah. You can say the same things about the natives. There could be differential fertility by economic productivity later in life, that kind of thing. If you were to do something to increase fertility replacement, who would have the babies? Then we get to the whole story of differential fertility and that sort of thing. Okay, so we have less momentum for migration scenario than fertility scenario. In a previously declining population, stationary population will be bigger, and you have less dependency too. Okay, I'm kind of perfect timing here because I have about 3 more slides that are mostly very discussion oriented. We already touched on a lot of the things. Okay, so let's first talk about realism and whether how crazy it is to have migrants enter at age 18. Well, it makes the math super simple because total migrant fertility, because they haven't had any kids yet, is the same as newborn fertility. There's very little mortality or anything like that. So the sum of future fertility for the migrants is the same as the sum of future fertility for the natives. And so it makes the analysis super easy. But what about somebody who comes in at age 30? What should we do with them? How should we model them? Well, one way to do it is just have that person come in at age 30. But I remember Carl Schmertmann has a model like this, and I think I objected to it in a Vienna colloquium long ago, and I said, wait a second, someone who comes in at 30 is probably going to come in with kids. So in some sense, the person who arrives at age 30 is like the person who arrived at age 18, but just 12 years later with their kids, but they're going to come with their kids. So it's not really fair, I don't think, or it's less realistic to have immigrants come in at age 30 without children than it is to have people come at age 18 without children. So once you start bringing in the 30-year-olds, you have to start thinking about, do they bring people with them? And then it's even more complicated because one phenomenon, I mean, the relationship between fertility and migration is interesting. Sometimes people come in order to have their children in the destination country. That happens sometimes. And sometimes people don't move when they have very small children. They wait till the kids are bigger so they can move. And other times, people say, I'm going to have children. Well, those are the kinds of dynamics there are. So it's very complicated. So I don't think we're really losing that much by having everybody come in at age 18. Instead, having someone come at age 18 is like having someone come in at age 30, 12 years later with their kids, in terms of the population dynamics. And of course, in terms of where the kids are born, it's different. People convinced by that? I'm not fully convinced by it, but that's my kind of intuition of why this is useful. Okay, and then to the kind of point about dependency ratios, you're getting some dependency ratio benefit. Well, in the NTA type of setup, where the reason that children are expensive is they take a lot of investments, education, parental time, all that kind of thing. Essentially, what you're doing is you're doing that out of the country, so you're not accounting for it. And you're benefiting from it. You're not paying taxes for the Swiss education system when someone from Switzerland comes in at age 18 to Austria. And so that's a benefit. But of course, you may not be getting the same human capital in Switzerland as you do in Austria, or in Afghanistan as in Austria. So it's a little bit of, when we just use age, we're pretending everybody's the same, but as Alexi pointed out, people can be quite different. And at least I'm not sure about Austria, but I guess it's similar to the US. In the US, the educational distribution, skill distribution of migrants, economic productivity of migrants, is much more dispersed than of natives. So you have a lot more very educated people and a lot more with very little education. It's much more extreme. So it's a combination of both things. On average, maybe it's the same, but maybe the averages aren't important. Anyway, it's something detailed that one needs to look at. And then, of course, we have politics. One reason to do this kind of sponsorship kind of thought experiment is because there's kind of a limit, we think, of how many immigrants a population is willing to take. And presumably that's proportional to the number of people that are there in some sense. Austria is willing to take more immigrants than Liechtenstein, and Germany is willing to take more immigrants than Austria. So, whatever the challenges of immigrants are, they kind of should scale to population size. Okay. Formal extensions, range of immigration ages, a non-stable start, look at this analysis of immigrant magnitudes like Mark was suggesting, where he said 1/3 of the people. Well, for different, how does that change depending on what age you let people in, on what the schedule is, all that sort of thing. We could, of course, just like we have gradual fertility momentum, where fertility doesn't change from year 0 instantly, it changes gradually over some time. You could have changing the migration regime gradually. You can also have alternative kind of formal models of where migrants come from, or what the level of migration is. Here I had it proportional to the kind of birth cohort size. You could have some constant number of migrants. That's been studied extensively, but you'd have to have some, this paper would motivate you to choose a particular size for that migrant stream to make it comparable. The UN's report on replacement migration a few decades ago did something algorithmic. They just let in the number of immigrants every year to keep the population stationary. So it's kind of like dynamic programming type of thing, where they just change the number depending on what how many births and deaths there were the previous year. So there are different ways to do it. I should say there's also much more substantive extensions. There's the whole kind of multidimensional demography part of education, and then there's, of course, the kind of eco-demo kind of full model of how this all plays out, and you could kind of get a sense of what would happen in much more complicated cases. Okay, so my discussion conclusion. A lot of the literature is pessimistic about immigration as a solution to population decline and aging. There's a lot of reasons for this. We can talk about why it's pessimistic in the discussion. Our formal analysis here, maybe just because we're naive and we're kind of starting from scratch, at least we don't know that much, it suggests otherwise. The kind of usual thing that we say, that a country that can attract productive migrants and keep them and incorporate them is going to be much better off than a country that can't. And this is kind of the other discussion in the United States, is this huge anti-immigrant sentiment, but there's also this kind of huge, what does America have? Well, one thing we have is the ability to historically have incorporated a lot of migrants and attract the best of the brightest from around the world, and so this is very consistent with that philosophy. More specifically, encouraging young people to come with their human capital and to build human capital and stay, it makes sense. A lot of countries have these policies. This modeling kind of explains why they might have that policy. Obviously, if a German comes to Austria and becomes a doctor and then goes back to Germany, it wasn't a very good investment, but some of them stay here, right? At least that's the argument. Maybe we should think about forming a sports team is kind of understand the intuition here, why migrants, what the advantage of migrants is. If you bring in a migrant, you can bring in someone who's ready to play in some sense. If you were forming a team, would you, get a 1-year-old or a 0-year-old and say, oh, I'm going to train them? Well, if you want them to be your football culture, this football team, then I guess you start with a 0-year-old. But if you're happy to take someone who comes from another place, then you would probably take the 18-year-old, and they're ready to play. And that's part of what's going on here. Okay, that's all I have to say.